Good morning, everyone, and welcome to AP Statistics. First, I'm going to go over the homework results from page 163. Here are the answers you should have gotten. Page 163, 27 to 32. A like apple, E like elephant, D like daffodil, B like brontosaurus, B like brachiosaurus, and D like Dilophosaurus. I have dinosaurs on the mind. Now, if you have any questions with any of those, you can either ask me in a comment in the email or save it for when you see me, but those are the answers to the prompts. Go over them, make sure you understand them. Okay, now, we're going to do a little reminder of what we did in class, which was linear regression. We're going to find the R and the R squared value. We're going to talk about interpolation, extrapolation, and whether the pattern is truly linear. So first off, if I give you a set of data, X and Y data, you put the X list into your L1 under stat edit. You put the Y data into your L2 under stat edit. You do not sort them, because if you sort them, you unmatch them and they need to be paired, because those are the coordinates. All right, now make sure your diagnostics are on. Either go to mode and go down to stat diagnostics on, or if it's an older calculator, go to second 0 for the catalog help and scroll on down to diagnostic on, turn it on. Okay, then we want to make sure that there's nothing in our menu already. So clear out anything that's in Y equals because you don't want multiple lines being listed. Then we're doing our regression. So stat calc 8, which is the linear regression A plus BX. You tell it to look at list 1 for the X list data, list 2 for the Y list data. Where it says store regression equation, you do want to tell it where to store it. So you go down there and you hit vars, go over to the right for Y vars, hit enter for function, hit enter for Y sub 1. That tells the calculator to store your equation in the Y sub 1 menu so we can graph it and then use it for predictions. Cool. Now, if you run it, you'll see the output, which tells you the format for the equation. So it'll tell you the A and the B. It'll also tell you the R and the R square. R is called the correlation coefficient, and it tells you the strength and the direction of the linear pattern. If it's close to +1, it's close to a perfect positive relationship. If it's close to -1, it's close to a perfect negative relationship. The more they edge in on 0, the less strong they become. Strength is really how close the data points are to this trend line, the least squares regression line, LSRL. And the closer the points are to the line, the better a predictive model that it is. The R square is called the coefficient of determination, and it tells you the percent of the variability in the data that's explained by the linear relationship of X on Y. Okay? We said that the X data can be called an explanatory variable, and the Y data can be called a response variable, if indeed there is a correlation that indicates that there is some sort of cause and effect. We talked about the dangers of using our model to make predictions, because after all, the weaker the R value is, the less accurate and trustworthy the model is going to be. If you make a prediction for an input within your domain, it's usually fairly safe, especially if the R value is above, let's say, 0.85. It's called interpolation if you make a prediction within your domain. However, when you make a prediction outside your domain, it's called extrapolation. And it can be okay if you have very good R and R square values, but the further away you get from your domain, the less reliable it is and the less you should have faith in your predictions. These are things you can actually say if you're asked to make a prediction based upon your linear model for a value that is outside your domain. You could say how well you have, how much faith you have in your prediction based upon the R square, the model, the story. I mean, if negative values are meaningless in the story and they ask you to predict for a negative input, you can find the output if you want, but you would say this is meaningless because in the context of the story, negative X values are impossible. All right, keep these things in mind. Now, what we're going to do right now is talk a little bit more about the values and let's say how good the predictive models are. So here's what I want you to do. I'm giving you some X and Y data, and I want you to do the regression on this XY data. There's not going to be much data, just 4 points. Okay, so here are our coordinates. We had -1, 1.5, 0, 2, 1, 3, and 2, 5. So what I want you to do right now is pause the video and do the regression on this list of data. And then when you're done with your regression model and all the steps I just said, you can unpause the video and check out what I got. So do that now, pause. So if you do the model correctly and you go through the process of regression, you get an equation that is y equals 2.3 plus 1.15x. I'm going to make one little correction to this, and it's in the equation's y value. I just want you to put a little caret on top. So that's called y hat. I know it's a ridiculous name for it, but it's what it's called. Y hat tells you you're finding a predictive value. It's not that the output y is absolutely going to equal 2.3 plus 1.15x. It's that we're predicting it to equal in the vicinity of 2.3 plus 1.15x. And the hat on the y indicates a predictive value. So use those from now on when using predictive models. Okay. So here's my question. How good is it? Well, let's see. We had an R square, because it listed first for some reason, of 0.92. And the R value is 0.9592. What's that mean? Well, 0.9592 for R means it is a very strong positive linear correlation. The R squared tells you that 92% of the variability in our data is well explained by the linear relationship of x on y. Okay, if you looked at the graph, which you could do right now if you hit the graph zoom 9, the graph looks kind of like this, where you've got -1, 1.5, so it's like over here, and there, and like over there. And if you had put the LSRL on it, it looks kind of like this. Okay? It's a good idea to make sketches of the values you're using. It's going to help visualize what we're doing. All right, so make a prediction. So here's what I want you to do right now. What is our prediction when we have an input of 0.7? And what is our prediction when we have an input of 3? So all you're going to do is either just use the equation that we have right there and plug in for x, or using your calculator on a blank screen, you could do vars, y vars, enter, enter, open a parenthesis and pop in the 0.7, enter, it tells you the answer. Then you could do second enter to go back into the input and change it to a 3, and it'll tell you the answer. So what do we predict here? Well, at 0.7, the prediction is 0.3105, and at 3, the prediction is 5.75. Now, 0.7, well, that's within our domain. So 0.7 is an interpolation, and we can be fairly confident in it. 3 is just outside our domain, so it's an extrapolation, but it's pretty close to our domain, so we can probably have faith in it. But here's what we have to do every time. There is the possibility that our data was not as linear as we'd like to believe. The way we check this is with what's called a residual graph. Now, you know that residuals, hopefully, are the difference between the observation and the expectation. So, for instance, in the little sketch I have here, the first and the fourth points are, I think, supposed to be a little bit above the line, so they have a slightly positive residual. And the second and third points are a little bit below the line, so they have a slightly negative residual. How do we find the residuals? Here's what I want you to do, and I'll show you on my calculator as well. Okay, so, you know what I should have done first is made sure I actually entered this data into my calculator, because that would be a better idea. So let me just do a little input real quick. Okay, obviously Again, a good idea to have done it first. But -1, 0, 1, and 2, 1.5, 2, 3, and 5. And I'm just going to run it real fast. Okay. There we go. So I got everything there. Now here's what I'm going to do. Ready? I'm going to go back to my stat and go to my edit, my lists. And what I want to do is go to list 3. And when you go to list 3, go up to highlight L3. We want the calculator to find out what the residual values are. So here's where we go for that. We go to second and then stat. And you should see, there's always a possibility you won't, but you should see somewhere at the bottom a pre-programmed residual function. It says resid. We'll go through what happens if you don't see it in a minute. Hit enter and enter again. And now it tells you the residual values for this relationship. What it's doing is it's taking the equation that you put into y1 and it's putting the L1 values in to see what the result is, and then it's finding the difference between that and the observation in L2, okay? If for some reason your resid function is not there, here's what you type in, okay? I'm just gonna clear this out for a second and show you what you type in. So highlight the L3. You want it to tell the calculator to do what I just said. Find what happens when you plug in the L1 into your equation. Since you stored it in vars, yvars, enter, enter, it now says y1. Open the parenthesis because you need to, and tell it to look at the L1, second one, as the inputs. Then close it. Now, I started off with the second part of the equation. So before we do that, and maybe you can go backwards, I'm just going to insert something. So I'm going to do insert. I should have started off with L2. And it's L2 minus. So here's what it actually should look like. And I apologize for that. It's L2, the observation, minus Y1 using L1 as the input. It's observation minus expectation. So that's kind of the order you do need. I apologize if I goofed you up on that. But if we hit enter there, we get the same numbers. Okay? So that's how you can manually enter in what is called the residual function if your calculator for some reason doesn't have it. Okay, all well and good. Here's what I want to do right now. I want to graph the residuals. So here's what we're going to do. Ready? First thing, go to y equals, and I want you to turn off this equation. So highlight the equal sign and hit enter to turn it off. I just don't want to graph it. I don't want to lose it, but I don't want to graph it either. And now we're going to go to second y equals to a stat plot, and we're going to turn on a stat plot. And I want the scatter plot, as always. X data is L1, but I don't want L2 to be my Y data. I want the residuals, so L3, okay? Zoom 9. Now, here's my residual plot. It's showing me something. There's something we're looking for in a residual plot, and it's called a pattern. If there is a pattern in the residual plot, your data is not linear. This data is not linear data. It has a pretty clear, almost parabolic curve inside the residual plot. So you would sketch this and say, the residual plot shows me that my data is not linear. What that means is extrapolation is not advisable. You can't extrapolate or predict with a linear model on non-linear data. So what is the data? Well, if you are in doubt, let's just take a look at the graph of the original again. So I'm just going to go back in. I'm going to change my Y list to L2 again because I wanted to see the data again, okay? And I'm even going to turn back on my equation. So turn back on the Y equals and zoom 9. Now, this is what the sketch looked like. You could probably see now that there's a curve to it. It almost looks exponential, doesn't it? Let's just run an exponential regression just to see. So I'm going to go to Stat, Calc, but I'm going to go all the way down to Exponential Regression. And I still want L1, L2. I'm going to store this equation not in Y1 this time. I'm not going to overwrite my line. I want to put it in Y2. So I'm going to say vars, y vars, enter on function Y2. And I'm going to calculate that. And I'm going to get an exponential equation. Now it's AB to the x. So it's 2.1187 times 1.4944 to the power of x. If it's exponential, take a look at those r and r square values. Those are amazingly strong. If it's exponential, the r is 0.9924, the r squared 0.9848. This is a very, very good model. Zoom 9 on this. There's the line of the LSRL, but here's the exponentials approximation of the data. Now that's pretty perfect. So here's the deal. This was an exponential model. If you wanted to figure out what the actual outputs would be, I'm going to go to, again, vars, y vars, enter y2, because I want to find out what my predictions really should have been. At 0.7, like we said, it wasn't too far. Okay. Okay, well, it wasn't too far. Actually, it was pretty far. At 0.7, it really should have been, I'll put it over here, 2.8067. That's the actual output using the exponential model. And what about at 3? Well, it was supposed to be 5.75, but it's actually 7.0711. These predictions are not good. The values are not good. Even the interpolation is not good, because look at the difference between the predictive line and the exponential line that it should have been. These values are not good. And extrapolating even further out, it's going to get worse and worse and worse because it's curving upwards for real, but a linear model would not have curved upwards. So there are definite hazards in extrapolation and even interpolation, unless we look at the residual plot. And again, a residual plot is showing you whether or not your data was linear by the presence of a pattern. What I want to see is a random scatter of points. What I don't want to see in my residual is any pattern. A line, a curve, a zigzag. It's showing you that there's something wrong. All right? And that's the lesson of the day. So what I'd like you to do is go to a website that I'm sharing with you on the Google Classroom announcement. It's called Spurious Correlations, and it's fun. There's no work. It's just fun observations. What the author has done is he's taken two very disparate data sets and graphed them together to find out that they're very well correlated, but meaningless. Have fun with that. It's actually enjoyable to flip through. There's no actual homework tonight. Enjoy it, and I'll touch base with you on Wednesday. Have a great day.